Hello students, good morning. I hope you have gone through the last lectures, video recording of the last lectures, and there I have introduced a very important topic, namely the probability distribution and distribution function of a random variable. So recall very quickly that if a random variable is a real valued function on a probability space, and for any random variable x, I can define a new function px which is different from this p. So p assigns numbers or probabilities to the subsets of s. S could be anything. It could be head, tail. It could be numbers like 1, 2, 3, 4, 5, 6, and so on. But x will take always real number, real value. Now p will assign probabilities to subsets of x. Now once we have x, then what will happen is that we will have a mapping from x to r. So therefore now what we will defining is a new function px which will assign numbers to Borel sets. So you know Borel sets, they are subsets of the real line, or they are sets of real numbers which are defined, which are members of the Borel sigma field. And Borel sigma field is the sigma field generated by open intervals, or you can say semi-open intervals, or open sets, or you can say closed sets, either way, and these are all equivalent definitions. So given any Borel set, I want to measure what is pxb. So that is called the probability distribution, and it turns out to be that since we know how to measure the probabilities of subsets of S using P, we make use of that. For any B, we look at the pre-image X inverse of B, so those points in the domain for which X is in B, and assign the corresponding probability P. Now this is the idea. Now probability distribution, why is it important? Because suppose x is the number, x is a certain variable of x represents certain variable of interest. For example, suppose x represents height or weight or water level or number of heads in a sequence of coin tosses. So all this we would like to know what is the probability that x is equal to a particular value y, or x is between a to b, and so on and so forth. So we want to measure these probabilities, so we need the px. Now this concept is similar to measuring lengths of sets. So just like what does Lebesgue measure does, it assigns a notion of length to any Borel set. Similarly, the probability distribution will assign probability to any Borel set. Now again, if you remember, I had briefly discussed there that the construction of so how do one define the length of any Borel set? So that starts with the idea of measuring length of an interval, and then you define length of union of disjoint intervals, and then you go on extending it, and finally via Carthaturi extension theorem you have a notion of length for any Borel set. Now so by the same process we can we can go on constructing, or we can go define the pxb for any b. Now now that story is a bit long, and it is a part of more advanced course measured purely when you do a measure theory, a measure theoretic aspect of the probability. But the point is that just like for Lebesgue measures, or just like for defining length of Borel sets, it is enough to know how do you define length of intervals. So and length of length of a set which is a union of disjoint intervals. In the same vein, for specifying the probability distribution, it is enough to know how do you define probability of x between a and b, and in that respect so it is enough to know what is called, we call the distribution function fy. So this is the last time I am repeating this story. After that there is no need. So we now understand that for every random variable there is a probability distribution, and for every probability distribution we need to specify fy probability x less than equal to y, where x is a random variable, and f is its distribution function. Then I asked you to verify that probability that x between a to b is f of b minus f of a, and that comes from finite additive property that we have proved earlier. Now I come to some properties of this distribution function, that is probability x equal less than y. So what we are now saying that it is non-negative valued, obviously, so because it is a probability and it cannot be more than 1, because we have also showed that probability cannot exceed 1. So therefore fy is a number between 0 and 1 because it is a probability. And now comes the first property, it is non-decreasing. That means if you take two numbers y1 and y2 where y2 is more than y1, then f of y1 cannot be more than f of y2. So that I wanted you to prove. So what you need to prove really is that probability x less than y1 cannot be more than probability x less than y2. In that way, I am giving you a hint that we have already proved a property that if A and B are two subsets of S such that A is a subset of B, that is A is contained B, then what is probability of A and probability of B? Can probability of A be more than probability of B? So that is the thing that we all know. And then you must question what is A. A is those points in the domain. Is those points in the domain for which xw is less than y1, and then B will be those points in the domain for which xw is less than y2. Now y1 is less than y2. So for any xw is a real number. If xw is less than y1, then definitely xw is less than y2. So that is the hints. So please write down the proof. I have told you all the arguments. So f minus infinity is 0 and f plus infinity is 1. This really follows from the first properties. Why? Because you see fy is, so you look at the sequence. So you look at this sequence, f of minus n. Okay, so you look at this sequence f of minus n. What will happen to this sequence as n becomes larger and larger? So this is a bounded sequence between 0 and 1, and f is non-decreasing. So as you increase n, this will also be decreasing. Because why? F of minus n minus 1 minus n plus 1 is less than minus n. So therefore by the monotonic property, monotonically non-decreasing property, f of minus n plus 1, so f of n minus, my keyboard is actually not working today, so that is a bit problematic, f of n minus f of 1, these cannot be more than f of minus n because of the monotonic property. So that is the main point. So you have now a sequence, you see you have now a sequence f minus n, so what is a decreasing sequence and bounded below by 0. Now only thing that you need to convince yourself that 0 is the infimum, or 0 is the greatest upper bound, greatest lower bound, correction, and 1 is the least upper bound. Similarly, what will be the relation between fn plus 1 and fn? Then fn plus 1 cannot be less than, so fn plus 1 will be greater than equal to fn. So the point is that f minus n will be a decreasing sequence and fn will be an increasing sequence, both lying between 0 and 1. Now you convince that 0 is the greatest lower bound of f minus n and 1 is the least upper bound of fn. That is also not very difficult to convince, because if you give me any positive proper fraction, since fn is increasing, so therefore you can always find an n such that fn will exceed that, value. So therefore you see, now you have a decreasing sequence f minus n and an increasing sequence fn, which is bounded between 0 and 1. So they will be convergent, and converge to f minus n will go to the greatest lower bound, that is 0, and f plus fn will converge to the least upper bound 1. So symbolically we say f minus infinity is 0 and f plus infinity is 1. So actually what this means is limit n tends to infinity f of minus n. So f minus infinity, actually it means it is the limit nothing is working. Paste. This is actually the limit So the f minus infinity, that is the limit, and so that's why this is the line of argument that this is a bound, f minus n is a bounded sequence, and it is decreasing, and therefore 0 is the greatest lower bound, and so it will be 0. And similarly f plus infinity, you can understand. So in now the more advanced property is that f is a right continuous function. So what f is a right continuous function, meaning what? That if I take the limit of z, where z is increasing from below, so I am increasing z from below y to up to y. So then what will happen? Again in this context, the monotonic property comes into play. So you see that what is the relation between fz and insert equation fz and fy, where y is less than z. I'm a bit slowed down today because the keyboards are not, all the keyboards are not responding. Y is less than equal to z. Let's see, less than equal to z. So you see, this is the main point, that whenever you give me, so y less than, let me put it z, because I am taking the right limit, no? So y is, insert y is less than z. So give me any number y less than z, then fy is less than equal to fz. So fy cannot be more than fz because of f is a non-decreasing function. So now again the same story, that now if you oh 1 minute, sorry, I'll write z, I'm increasing y, right? So I made a mistake here, y. So where z is less than y. Sorry. See, even the brackets are not working. It is so frustrating. Copy. Paste. So that is the main thing, that if you give me any number z which is less than y, then fz cannot be more than fy. This is coming from the non-decreasing property. Now if is a, again now here f as a sequence in z is a increasing sequence which is bounded above by fy. So by that logic it will converge to the least upper bound, and in this case you need to argue that fy is the least upper bound. So therefore the fz sequence when z is increasing up to y, then it converges to fy. Therefore this is the right continuous function. So you see here the central property that is being used is that f is non-decreasing function. So f is a positive proper fraction valued and non-decreasing function, and it is right continuous. Now I will leave here what is this. So you need to prove that fy minus, this is the left limit at y, this is equal to probability x equal to y. Now here also you will need the finite additive property, And one last hint, that what will be probability x equal to y when x is continuous.